is a first law problem. So the first thing I do is remind myself it's a first law problem. Now, this is the only kind of problem we're dealing with right now, but that's only going to last a couple of days. So remember, right now, all you're looking for is whether the object is accelerating or not. That's what makes it decide. That's how you decide if it's a first law or second law problem. The next thing you have to do is you have to go through, reduce each object in your problem to a dot, and begin to draw arrows indicating the types of forces that are acting on the object. You have a list, and they all have very specific references as to whether you would draw them or not. The first one, is there a conservative force acting on the sign? Yes, so I will draw a single arrow downwards indicating there is a conservative force acting on the sign. That is the weight of the sign. Is the sign in contact with any surface? If it is, you draw a force that is perpendicular to the surface in contact. Is the sign attached to any cables or ropes or strings? If so, you'll draw arrows in the directions of the cables or ropes or strings. So there's no normal force here, but there's certainly a force to the right. And if you're unsure as to how long to draw a force, you should be unsure. You should be asking yourself, how long should I draw each of these? I probably should have drawn the other force first, since I think it's going to dictate how big I should draw each of these forces. Because I need to make sure that this force pulls up as much as the weight pulls down. And I established the weight first. So I think that's got to be T2, because I need this to be the same size as that. Which means I probably should adjust T1 and make it a little bit longer. There we go. We're trying to ensure that we're striking balance. For everything that's left, there's something right. Everything up, there's something down. I've gone through the contact forces. I go down to resistive forces. There's no air resistance unless it's told to us in the problem. And friction, well, it has to be in touch with this surface in order for there to be friction. Friction doesn't exist without a normal force, and there's no normal force here. So this is it. This is the end of my forces. I've drawn all the forces. This is a free body diagram. If all you're asked to do is draw a free body diagram, it ends here. But we're not ending here. We're going to apply a coordinate system. You have two priorities upon which to apply a coordinate system. Number one is you line one of the positive directions with the direction of the acceleration. The system's not accelerating. I don't have to worry about priority number one. Priority number two is trying to line it with as many forces as possible. I have two forces that are already at a right angle to each other. That seems like my guiding principle right there. I will align my coordinate system so it's aligned with those two forces. That suggests the y direction, something like this. In the x direction, something like that. We'll call this the positive x. This is the positive y, the negative x, and the negative y. I am clearly marking the directions that are positive and negative and clearly labeling everything. Now in your class, I combine step 3 and 4 because this is mechanics. So I break the other step out in AP Physics 1. But for us, drawing in the coordinate system and breaking up off-axis forces into components is really one step. I have one off-axis force. And based on the angle being theta there, I know that this has to be theta here. I know that because I remember my geometry, and I'm sure you guys do too, that these are alternate interior angles and therefore must be the same. You remember your geometry, correct? Are you hitting play or are you turning play off? Good idea. Maybe headphone out. Should be slyer than that. Now, to break this up into components, I'm going to draw a component that is horizontal. I'm going to label it TX. I'm going to draw a component that is vertical. I'm going to label it TY. I will only do this one time. This is the adjacent side. This is the opposite side. This is the hypotenuse. Sine of theta equals TY over T2. And cosine theta equals TX over T2. I'll never do that again. You guys need to be able to do your trig. But this is what I mean when I say you have to break it up into components. You're always going to be taking a vector and scaling it by sine and cosine. Make sure you know how to do that. So that means ty is t2 sine theta, and tx is t2 cosine theta. All right, we're all done applying those steps except for step 5. And step 5 says to take my Newton's laws and apply it to this problem. So I separate Newton's law into net force in the x direction and net force in the y direction. It's a set of instructions that says to add up all of the forces, taking into account their direction, and set them equal to, in this case, 0. So in the x direction, there are 2 forces. T1 points to the right and is positive. Tx points to the left and is negative. And Tx is T2 cosine theta. That equals 0. Next, y direction. I have T2 sine theta pointing upwards. That's in the positive direction. I have weight pointing downwards. When you are done, you'll get one of these for each of your Newton's law formulas. It's a relationship that could be used to solve something for your problem. This one can be used to figure out how much tension is in each cable. I would think that the tension would be based on how heavy the sine is. Since this is our ultimate goal, it should be clear that there's stuff to do here. There's ways to figure out what T1 and T2 equal. You guys have done lots of algebra. You should be able to see a pathway to figure out some answers here. Maybe substitution or something like that. Now, this is not what I will ask you to do tomorrow. Your problem will stop here tomorrow. But this is mechanics, and I expect you guys to be able to do things. And these are just some things. We'll learn about this kind of stuff, but if I want T1 and T2 in terms of the weight of the object, I can do that right here. I can divide both formulas. This will eliminate T2 and give me weight over T1 equals sine theta over cosine theta. What's sine over cosine? All of you should know that. It tells me pretty much that T1 is equal to the weight divided by tangent theta. That's what it tells me. So if I'm trying to find out the size of each of those forces, T1 and T2, this is how it's done. All right. This is what I want to see tomorrow. Ready for your next example? All right. Example number 5. I have a wagon being pulled by a child. What? A wagon can be pulled by a child, that's okay. The child applies a force at some angle to the wagon. The wagon has mass M. I would like a free body diagram for the wagon. In fact, I'd like you to apply this set of instructions to the wagon. The wagon is moving this way with a constant velocity. All right. So downward force for weight. And just because the picture has a obnoxiously large pulling force doesn't mean yours has to have an obnoxiously long arrow. Your arrows are supposed to be drawn to mimic what you believe is the appropriate length forces to deal with what's happening here. Is the kid actually jerking the wagon out off the ground? Then perhaps your pulling force should be appropriate for the size of the wagon. So unless it's lifting the wagon off the ground, your pulling force probably is going to be less than the weight of the wagon. But the ground is also pushing on the wagon upwards. And it's the combination of these two upward forces that should equal the length of the wagon's weight. So this height and this height should together be about that height. That gives you appropriate balance up and down. Now, I do think it's not a terrible stretch to think there must be some resistive force this direction to lend balance to the problem. And the length of this is attempted to look like the length of that. And I'm going to label this one friction. These appear to be the forces that are acting in our system. Reasonably, I don't think there's anything else to add. So I will add a coordinate system to help me deal with these forces. It's not accelerating, so I'm going to choose a coordinate system that's aligned with the most number of forces possible. I can align it with 3 of the forces. I'm going to draw a positive x, a positive y, a negative x, and a negative y. That way, any grader in here will be able to easily determine what you are saying is positive and negative. And we're putting it right on our diagram. I'm going to recognize that from the picture above, that has to be the length and the angle of my applied vector. Because I'm about to do trig, I'm going to write this over here to get it out of the way from the fact that I need to put a component of the applied force in this direction and a component of the applied force in that direction. This is the sines component, and this one is the cosines component. One's adjacent, one's opposite. So I have taken my off-axis vector and broken it up into components. So now all that's left is a net force in the x direction equal to 0, and the net force in the y direction equal to 0. There appear to be 2 forces in the x direction. I have Fa cosine theta minus friction equals 0. There appear to be 3 forces in the y direction. Normal plus Fa sine theta minus weight equals 0. Any questions to this yet? Yep? No, it doesn't matter. Now, there's some simple follow-up questions, like with how much force would the kid have to apply to lift the wagon off the ground? That's contained here. It's right here. If I want to lift the wagon off the ground, I want to reduce the normal force to 0. That's when the wagon is lifted off the ground, when it's no longer touching the ground. Things to start adding into your notes will be things about what are known as reactive forces. The normal force reacts to the conditions of the problem. It has to be enough to keep the object from sinking into the ground, but it only provides as much force as is necessary. The kid's both pulling upwards on the wagon and the ground is pushing upwards on the wagon, but the weight of the wagon is fixed. The kid pulls hard enough, he lifts the wagon off the ground. So understand, you will have to make these kinds of decisions. When do you know? When the kids pull the wagon off the ground? When the normal force goes to 0. That's when the wagon's off the ground. There'll be no friction then either, right? If it's not touching the ground, there's no friction. Ready for the next one? I'm going to intentionally try and trick you with this one. Don't be tricked. I have an elevator with a person standing inside. Person 60 kilograms. The elevator is moving upwards with a constant velocity. I would like the free body diagram for the person in the elevator. All right, the vast majority of you have 2 arrows drawn. Some of you have done this correctly, but some of you, no. I like the fact that when I walk around, I can count on the fact that most of you at this point have acclimated to the fact that there's a downwards arrow known as the weight. Good job. I'm going to add some information real quick. This person is 60 kilograms and acceleration of gravity is 10, which means their weight is 600 kilograms meters per second squared. That's the unit of force. Kilograms meters per second squared. We call this a Newton. Newton is the unit of force. It's a complex unit. Kilograms meters per second squared is the actual unit, but we call it Newton because it's easier to say that than kilograms meters per second squared every time. 10 newtons is about 2.2 pounds. So pound is the English unit of force. You tend to think of pounds and kilograms as being the same, but pound is actually a measure of force. So if you're trying to convert your weight to newtons, this is how you might do it. Many of you drew an upward force too. That's good, there should be one. The person should be in balance because the net force is going to be 0, traveling at constant velocity. It's what you put here that might be the problem. This is a normal force. There's no tension. The cable's not attached to the person. The cable's attached to the box. The person experiences a force of contact with the floor. By definition, that's a normal force, and it needs to be perpendicular to the floor of the elevator. Didn't trick many of you. So let's see if my next one tricks you. Draw the forces acting on the elevator. So again, a kid is pushing the box up a ramp. The ramp is angled theta. Box has mass m. I mentioned a free body diagram for the box. We have limits on time today. You need to be nearly done here. I know some of you are diving into your notes. Did you draw a downward arrow? Did you label it weight? That's a good place to start. So now that we have the conservative force out of the way, is the object in contact with the surface? So I think there should be a normal force. And by definition, normal forces have to be perpendicular to the surface. So, normal force. The kid's pushing on the box. No matter how you want to write that, no matter what type of force you label that as, I'd probably label it as another normal force since he's a surface, but normal force from the person, normal force from the ramp. You can just say a pushing force. Remember, these letters are here to help you identify and differentiate one force from the other. Did anybody draw in a frictional force? Really interested in the direction you might have drawn that. But I'm pretty sure if there's friction involved, it should be that way. You should oppose the box sliding up the ramp. Coordinate system aligned with the ramp would make the most sense. There are 3 forces that are all perpendicular to each other. That would probably be the best route to go.